use information from here for this. And if you don't know where it is, well, I want you to think about it for just a minute. How much of an oscillation is to be equivalent of going from here, where it's at maximum speed, to here, where the velocity is 0? So what is pictured is one way rougher than I intended. Now, if you have this, I want to talk about a few things, but that took way longer than I intended. Way longer. You should be able to flesh this out for a pendulum. I shouldn't have to direct you. You should be able to figure out what this would look like if we were looking for a pendulum and its properties as compared to a spring mass oscillator. Do so, please. What would this look like if I was trying to apply this idea to a pendulum? And if you still look at me like you have no idea what to do, then I'm really nervous. Sorry, but I couldn't trust you guys to do it on your own without me doing it. I don't have that kind of time. I was a little nervous just to look on some of your faces. But something like this is what I was expecting you to do. If this is equilibrium over here, then our pendulum should be doing similar things relative to equilibrium. They are similar devices. And as I said, all oscillators behave in a similar manner. Here is a similar manner. I've pulled the pendulum outwards a little bit and released it. And I've released the pendulum at time equals 0. At this moment, the velocity of the pendulum is 0. We might consider looking at it from angular velocity, not linear velocity. There's good reason to do that because it does have rotational qualities. I'd also argue that the kinetic energy is 0 because the velocity is 0. Where's all the energy if it's going to be in potential this time? Yes, sir?
Would the elastic potential energy?
There's no spring here, so probably not. Yeah?
Gravitational.
Gravitational makes sense here. We probably have something like mgh. But we also know that there's an angle here, right? This is theta max, the amplitude. If you don't remember, there's a way to figure out the gravitational potential energy based on an angle measure. It was way back first semester, and if you don't remember what it is, I'm willing to tell you. It involved the 1 minus cosine theta, and knowing that this was L, the length of the string. So our system starts with no kinetic energy, all potential energy. And at this moment, the torque on the system is max, the acceleration on the system is max, and the displacement of the system is at a max. All the same things we had for the spring mass oscillator, but for a pendulum. Release it. It's swinging, so it has some velocity now, either angular or linear, however you want to mark it, which means it has some kinetic energy now, either 1/2 mv squared or 1/2 I omega squared. Either one of those will work, depending on how you want to take your measurement. But at this same moment, it has some value for theta, some value for alpha, and some value for torque. It's easier to deal with a pendulum in regards to torque than it is force. All of those, though, are happening right now. And the energy is mixed, right? There's a little bit of gravitational and a little bit of kinetic, and that has to equal the total that we had at the start. All oscillators behave the same. This moment here has to be the moment where we are at 1/4 of the period. We've gone from maximum displacement to the equilibrium position. Here, velocity is at a max. Doesn't matter whether we're talking about linear velocity or angular velocity, velocity is at a max. All the energy is in the form of kinetic energy, and there is no gravitational potential energy. At this point, torque is 0, acceleration is 0, and theta is 0. And I think you should be able to fill in the rest, right? Have a nice day. I think I'm going to start this class's discussion a little different than first periods, because what's missing is a certain amount of context. And I don't mean this in a flippant way. I just mean this in a, how is the test going to be? Unlike the other units we've had, which generally are very thorough about your knowledge base required to answer the questions. Simple harmonic motion, they don't dive very deeply into it on the test. To be honest with you, I could show you the two formulas, and probably 90% of what's on the test is in those two formulas. And I mean, the one for period for a pendulum and the one for period for a spring mass oscillator. But I'm going to show you kind of the scope of some of the things that I would expect you to be able to do. So let's say that this is 3 kilograms traveling at 3 meters per second, and it strikes this spring. And when it does, it compresses the spring. Well, let's stick with my motif here. It compresses the spring 30 centimeters. There we go. So a lot of 3s in there. So it compresses the spring and comes to rest after compressing the spring 30 centimeters. All right? Everybody understand what I'm asking? Oh, I'm sorry, everybody understand what the dynamics are? I haven't asked anything yet. All right. I would like you to figure out what the spring constant is. And I would like you to tell me how long does it take for the box to come to rest after it hits the spring. One of those requires stuff we knew from last year or last semester. One of those requires what we talked about yesterday. Let's see if you can do either of them. You do have to solve this one before you solve this one. Now with the unit, you don't need to know anything from the prior unit. What kind of energy do I have here? Kinetic. Yeah, that's right, just kinetic. What kind of energy do we have here? Elastic potential. There's an interaction between the spring and the box, so we have elastic potential. Any loss of energy to any outside sources? I don't think so. So 1/2 mv squared equals 1/2 kx squared. That's it. So that's a little disappointing that I didn't see this across everybody's. It was even in yesterday's discussion, but come on, this is first semester stuff. So Garrett, what'd you get for K?
I got 300.
Anybody agree with him? Seems too easy, 300, but it probably is right. All right. Did nothing but threes here. I can't imagine it'd be anything else, right? 3 times 3 squared has to equal some 3 times 0.3 squared. Seems reasonable that 300 would work out. So do I need to work it out? All right. So that's 300 newtons per meter. Don't forget the unit of the spring constant. It's newtons per meter. Right, the idea is how much force does it take to stretch the spring? So this is what we have, 300 newtons per meter. Now the next question I'm asking is for you to figure out how long it takes to come to rest. Can't use a motion equation for this, but you being pictured here. Yes, sir? 1/4. That's right. We're going from maximum speed to 0, that 1/4 of the period. 1/4 of the period. You know how to calculate period, or at least you were shown the expression to calculate period. Period for a spring mass oscillator is 2 pi times the square root of m over k. I want 1/4 of it. So, now at this point, the secret is out. So there's nothing particularly interesting. But this is it, right? It's not very much. Now, does this seem like a whole lot of simple harmonic motion in this question? There's not a lot here. But there are people who want to use something like this to solve that. And you understand you can't. Acceleration is not constant. You can't use this kind of motion equation. You have to use the expression for period, which is why I spent so much time talking to you about all the different points of motion. Now, we have more to discuss today, and we're going to do some more practice, but let's do a little bit more practice real quick, just to make sure we're all dealing with the same thing. Period of a pendulum is 2 pi times the square root of L over G. We haven't talked as much about the pendulum, but we have talked a little bit about it. When asked what size pendulum would be used for a clock, retorted with, well, what are we doing this? Should it be in hours, minutes, or seconds? I find that silly. And I find it silly because I want a clock that fits in this room. And so if you put in the 3600 here for T and tried to figure out a pendulum that would tell you the hours, meaning it would swing once every hour. So you wouldn't know anything in the middle, but every time it finally came back, it would be time to advance the hour hand. This is what you would get. This would be the length. This is a big number, isn't it? Yes. Let's see. Let's see how many versions of this number. I saw 6 on my trek around the room. This is 3600 divided by 2 pi squared times 9.8. I'm still concerned that you won't all get the same answer, but at least we're all on the same page. And no, I'm not doing my algebra for you. Come on. You guys say you're smart. You guys say you want A's. I'm not doing algebra for you. And everybody should have the same answer now because I've done all the math for you. So I should be able to pick on anybody. They should all give me the same number. You better check with the person next to you because I am calling somebody out. Mostly because I'm a little bit frustrated. All right, Reese, what'd you get?
I got
3, 2, 1.
7, 1, 5, 0.
Cameron, what'd you get?
Not the same exact thing.
Same exact thing. Pierce, what'd you get?
Same thing.
That's 3 votes. Now, that's 3 million meters long. I'm thinking that might be a little bit too big to make a clock. So I'll ask again. How long is the pendulum in a clock that you could have in your room? Be realistic now. What do you think is being ticked off by the pendulum? Hours? Minutes? Seconds? What would make the most sense? It's got to fit in your room. If you still don't understand, try minutes. Put 60 in there and see how big it has to be to have a period of 1 minute. Trust me, it's going to be a big house.